Okay. Hi, everyone. Welcome to Happy New Year. Welcome to our first One Word ABC talk of the year. And it's my pleasure having here Antoine Luciano, who will talk about insufficient Gibbs sampling.
Thank you. Happy New Year to all of you. So that's a pleasure for me to present my work today. Thank you for attending this session in person in Paris or online. And thank you to the Christian and Massimiliano and the organizer for giving me this opportunity. So today I will present insufficient Gibbs sampling, which is one of my first research topic during my PhD. So I'm in PhD in Université Paris-Dauphine under the supervision of Christian Robert and Robin Ryder, who are both here today. And I will talk about insufficient Gibbs sampling. The preprint is available on arXiv, and the paper just got accepted in statistic computing, so it will be published soon, I hope. So, elles sont belles les photos. Okay, the picture are validated. It's okay. Everything is right. So, first, let me introduce the framework we are operating within. So we suppose that our data X, so we consider a parametric distribution. We are in a parametric framework. The user has to choose a parametric distribution. So here we can consider a wide range of parametric distribution because the only thing that we have to do is to know how to sample from a truncated version of it. So basically we can consider all the continuous distribution with compact support. So we suppose here that for some reason we don't have access to our data, and the only thing that we have access to is robust statistics. So here the term robust stands for quantitative robustness. So basically it's robustness to outlier, and those robust statistics that have some high breakdown points. So it means that you can change a part of your data without changing too much the statistics, are typically insufficient. And here, for example, we will consider the median, the MAD, and quantile. So basically, it's statistics that are based on order statistics. So our main goal here is to sample from the posterior, not given the data because we don't have access to it, but given what we have, and what we have is those robust and insufficient Gibbs robust statistics. Sorry. So the motivation for this work were twofold, if I can say that. So the first one was theoretical because in a lot of ABC paper, we can say that, we see the example of the Gaussian case with when we only observe the median and the MAD. And the other motivation was more practical. So because a lot of real data for privacy reasons are not fully disclosed. It's the case for income data, and we only have access to summary stats, which are quantized. So it was the other part of the motivation. And for the previous work, as I said, there is a lot of ABC inference that has been made, but just to be clear, because we are here in the one word ABC and not MCMC, here we just targeting the same posterior, but here we will suppose that our threshold is equal to 0. So we will target the exact posterior theta given the observed statistics. So this posterior can be decomposed while using X as a latent variable. So we end with that two-step scheme, which is the typical framework for augmented MCMC. So first, we will have to simulate augmented data given our observed statistics. So basically, we sample data that follow the distribution f theta and that present the same statistic that the one we observe. And then we have this data. It's quite simple to sample from the posterior given those data. So this led us to a Gibbs sampler, so because we have two full conditionals. So this kind of work has already been done in Lewis, who did his PhD about restricted likelihood, but he focused on the linear regression framework. And here we will just like sample, we will consider the case on parametric distribution, which are more general. So just to explicit our Gibbs sampler, we observe some statistic. We have to initialize in a really arbitrarily way both our data and our parameters, and then we have those two conditioners that allows us to sample from the joint distribution, the joint conditional distribution of theta and x given our robust statistic T0. So as I said, the second step is really straightforward, so it can be with in closed form for the case of conjugate prior, but it also can be done with metropolis hastings. Since we know our density f theta, we can perform metropolis hasting in a really easy way. So during this presentation, I will present our methodology for a different kind of robust statistics. So I will present the quantiles case, which is simpler but really helpful to consider some real data, real world data such as the income data. We'll also really quickly talk about the median interquartile range case, and the most interesting case is the case when we observe the median and the MAD. Then I will talk about numerical results, and some of them are quite amusing. And then I will briefly discuss about model choice, because surprisingly, with only those robust statistics, in some cases and in some particular cases, we can still do some Bayesian model choice. So first, let's suppose that we observe M quantiles, so with respective probability P. So here we can first suppose that our quantile are theoretical quantiles. So we will have this kind of theoretical apportionment. So basically, we can partition our support in n+1 intervals and have this kind of theoretical apportionment. But as I said, we observe here robust statistics that are not empirical quantile. They are computed by with an estimator, so they are empirical quantiles, and we will consider it as empirical quantile, which is the main difference between our work here and the work that has been done in quantile matching case with MCMC. So we will consider the most used definition, which is presented in Heinemann and Fan. So all the definitions are quite similar, but this one is used by default in R, in NumPy, in Julia, in Excel, in all the famous software that we all use. So this definition is like basically a linear combination between two order statistics with G playing the role of the weight. So here, if we observe M quantiles, so if we are lucky, our observed quantile will be just right on an order statistic, which is quite a rare event, because when n is quite large, it's like basically never happen. And in most of the case, we have like the observed quantile is determined by two order statistics. And so to sample a vector that's present the right observed the right empirical quantile, we will have to sample one of the two coordinates for each quantile and then obtain the other by a deterministic transformation, which is quite obvious. So here we will perform, oh, it's like a comma. I should have put a comma here. We want to perform like full resampling at each Gibbs step. So we want to resample the full vector. It's a choice we can do in really different way, but it's the thing that we implemented. So first we have to run at most M Markov chain for one order statistic for each quantile. Fortunately, we can compute the joint law of all of those order statistics conditioned on the observed quantile. So with that formula, and we just have like a variable change, we end up with the right conditional distribution, and then we can, like, using a metropolis testing step to simulate the Markov chain, and then we just have to complete our vector by simulating the right number of simulation in the right interval. So because it's only morning, I did like an ugly TIX figure to explain. So we have our xt vector, which is initialized like as you like. It can be a really naive way. So we perform our metropolis hastings step to update the order statistics that influence our observed quantiles. Then in a deterministic way, we can update the other. So as I say, one quantile is determined by two order statistics. And finally, we can just complete our vector by sampling with truncated distribution the right number of observation in each interval. So in that case, we have like kind of a Markov kernel between two vector, and at each Gibbs iteration, we fully resample our vector. So when I talk about resampling, it's not the resampling as the SMC sense, it's just that we consider new data are at every step. So there is also the median interquartile range that can be easily implemented with the same idea. So the difference here it's that we don't observe our quartile, we just observe the difference between the first and the third, and then it allowed this interval. So we don't have a fixed interval anymore. This interval can move, but the idea is quite the same. So I will move on because I want to talk about the most interesting part and the thing that was our first motivation when we discussed it. So which is the median MAD case. So here we suppose that we observe the median and the MAD. I guess that everyone knows the median, which is like a robust estimator of the location. But its cousin, if I can say so, it's less known. So the MAD stands for median absolute deviation. There is also the mean absolute deviation, but here we will talk about median absolute deviation, which is basically the median of the distance to the median. So basically, it's just a robust alternative to the standard deviation. So with those two observed statistics, what's the information that we got about our vectors? So first, we have the median at the constraint that we want to have half observation on both sides of the median. The MAD, so typically we want to have half our observation to have a lower distance to the median than the MAD. So we want to have half our observation in this interval. So with that two constraints, we end up with that theoretical apportionment. which is not fixed like in the quantile case, because there is this variable p that controls the apportionment between the zone 1 and 3 and the zone 2 and 4. So this is still a theoretical apportionment, but as you can guess, the median is like quite different in the odd and the even case. So the MAD is based on the median. So we have two different cases. And because we are lazy and obviously the odd case is simpler, we will focus on the odd case, but the even case is explained in the paper. So in that case, we have two coordinates. So one that is equal to the median, so we call it xmed, and ones that determines the MAD. So typically it's an observation which has distance to the median equal to the MAD. So we can turn our theoretical apportionment into a practical apportionment of our vectors. So we have this apportionment, which is in practice in every vector which have a median M and a MAD S. But the tricky, if I can say so, thing is that we have this variable K that controls the repartition of our simulation between the zone 1 and 3 and 2 and 4. And we have this delta that capture on which side the xmad is. So typically we have those two vectors. So those two vectors that are quite different have exactly the same median and MAD. So for K equal to 1, we have all our data in the interval 1 and 3. And for K equal to N, we have all the data in the interval 2 and 4. So the problem, as I said, is that to our knowledge, we don't know the law of K and delta, so we can't perform a full resampling as in the quantile and interquartile range case. So what we first thought about was partial resampling, and we say, like, what if we pick just one coordinate and resampling it? But if we do so, the repartition, so the K and the delta, won't move, because you can't move one observation without changing the MED and the MED. So what we thought a lot, and we find out that we will do that for two coordinates. So basically we just pick randomly or not, as you like, two coordinates, and we update them in a way that it doesn't change the median and the MAD of our vector. So with that methodology, we end up with an ergodic Markov chain on our data that fully explore our latent space. So this distribution is quite awful, so it has a lot of cases, but it's not complicated. It's just like truncated distribution all the time. This is quite awful, and because it's still early morning, I will just explain a few cases. So first, let's suppose that we are lucky or not, as you like. We just randomly picked xmad and another random coordinate. First, if they are in the same side of the median, basically you can't change xmad without changing the median. So basically xi will have to stay in the same interval. Now let's suppose that it's xi and xj are in different sign. Then you can perform this kind of moves. So we'll first resample xi, and you can like resample in like the symmetric zone, and then you have to change xj by its symmetric. So basically, this step is the step that can like change our delta. So turn our delta, which was equal to 1, to 0. And the other case, which is more likely, which has a higher probability if we picked two observations in the zone 1 and 3. In that case, we can resample xi on the full support and then perform this kind of move, which has like which change the apportionment and change the value of k. So that's why we perform a partial resampling of two coordinates. And obviously, at each Gibbs iteration, you can perform many update of two coordinates, many resampling. So if you're not convinced about my explanations, I can show you this little animated graph that say that even with a really naive initialization, so there is the value of k and there is the value of delta. So we see that our k is converging to a value which is equal to n divided by 2, because the Gaussian distribution here, the sample is Gaussian, f theta is the Gaussian distribution, so it converges to this value, and you say that you can see also that the delta is like changing. So this is for 100,000 simulation. You see that our latent space is explored. So now let's switch to numerical results. So, and I will first consider the Gaussian case that I just talked about, because it shows like interesting properties which are quite practical in that case. So first, the normal inverse gamma conjugate prior, which allows us to know the posterior in closed form. So we have this posterior, but also some asymptotic properties. So first, the Gaussian distribution is symmetric. So the median is equal to the median is equal to the mean. Sorry, and there is a linear relation between the standard deviation and the MAD. But furthermore, there is, as I said, robust statistics, such as the median at the MAD has higher breakdown points, but are insufficient. So we can quantify the quantity of information that they bring by their efficiency and their asymptotic efficiency, and hopefully and fortunately, sorry, in the Gaussian case, they have been computed. So we have the asymptotic efficiency of the median and the MAD that are known. So now let's just like doing like a sort of plugin thing. So we have those properties, and we want to build an approximation of the law of mu sigma given the median and the MAD. So the law that we sample from with our insufficient Gibbs sampler. So basically, if we just like change the mean and the empirical mean and the empirical variance in the normal inverse gamma posterior, we end up with that quite not that interpretable thing, but we can say that by just understanding that we observing the median and the MAD is like observing two vectors of different size. One is brings information about the location, and the other about the scale. And if we just like take our sample from the insufficient Gibbs, which I'll call robust Gibbs here, and our normal inverse gamma approximations for n not that large, it match pretty well. So as I said during the introduction, we wanted to target this exact posture to avoid the ABC approximation, which is like with a threshold which is positive. We have like some approximation. We implemented our insufficient Gibbs sampler to target the exact posterior, and we discover in practice that we can pretty well approximate it with like a normal inverse gamma. In the normal inverse gamma, we can approximate it pretty well. So now let's just quickly talk about real data application, because it was one of the motivations. So I selected a small village in the south of the French, totally randomly, from the income database from INSEE, which is the French institution for data. And as I say, totally randomly, I chose Comte, which is incidentally the birthplace of my grandfather, and a really lovely place. And by considering so the 9 deciles and the 2 quartiles, so we observe 11 quantiles, and we can perform our insufficient Gibbs sampler with the truncated Weibull distribution, which is a distribution which is translated, Weibull distribution, which is a distribution that is used to modelize income data. We can say that increasing the number of observed quantile, we identify some parameters. So it's just to answer the motivation that we have for real data. So now, I don't know how much time I have left, but I will talk about model choice. So as you all know, in model choice, we want to compute the probability of one model from to another. So to do so, we compute a base factor, which is defined as follows. But here I will present the bridge sampling estimator, which was introduced by Ming and Wang. Yeah, sorry. Ming and Wang, sorry. So which is defined as follow. We just like reparameterize our two marginal likelihood as expectations, and so we can use some sample from both of the posterior of the model to compute these two Monte Carlo estimators. So one thing which is important is that in the two model, you sometimes have to reparameterize it, because theta have to play the same role in both model. And by choosing a right positive function h, we end up with that iterative scheme, and it's like produce a consistent estimator of the base factor. So now let's talk a bit about ABC, because in ABC there is also a lot of literature about Bayesian model choice. So in Grelot and al. In 2009, they present that when we perform ABC model choice, we are not in a lot of cases we are not targeting. We are not like considering the base factor given the data, but only given the summary stats Tx that we use. And in Didlot and al. And Robert and al., they explained that they explained the relation between those two. So there is no T here, I'm sorry. So the base factor can be expressed in this way. Yes, I guess. Oh, yes, there is no T here, sorry. And so even when our Tx is sufficient for both models, so it can be sufficient to do some parameter estimation, but it's not sufficient to do some model choice. So it has to be sufficient across both models, which is the case in Gibbs random field, as explained in Crello and al. So as a motivation for model choice in that framework, so it's like still an ongoing work, but I considered the example in Marin and al. So they say that with ABC model choice, you're not considering the base factor based on the data, but the base factor based on the summary statistic that you chose. But this base factor could have consistency on some of assumption, and this the condition that they bring in Marin and al. Is that the asymptotic mean of those statistics has to be different between the two models. So basically, they bring the example of the normal Laplace case. So in that case, we want to do model selection. We know the variance, so those two models, it is a Gaussian case, Gaussian model, believe me. They have the same mean, the same variance, and we want to perform like model choice. So something which can be quite straightforward is to consider the mean, the variance, the first moment and the second moment, so the mean and the variance. But that doesn't work, so because, as I said, they have the same asymptotic behavior under the two models, so they are not sufficient for model selection. So they explain that it works by considering the MAD as solely the MAD as a summary statistic, and so they see that this is the probability of selecting the Gaussian model. So when it's Gaussian, you have a high probability, close to 1, to select the right model, and when it's Laplace, you have a pretty low probability of selecting the wrong model. So as they say, Bayesian ABC model choice could work with the right summary statistics. So now let's go back to bridge sampling. So, and in our case, we sampled from the joint distribution of theta and x given our statistics. So we have samples that follow this distribution. And if we just like put that joint posterior distribution in the bridge sampling estimator, we end up with that kind of thing. And in the same example, not exactly the same example, because here we consider the median and the MAD. In the case of a normal Laplace, we see that we perform the right decision. So we have a high probability of selecting the normal when it's normal, and a really low probability when it's Laplace. So it brings like a method to estimate the posterior without the approximation that ABC model choice brings with the threshold and the tolerance level epsilon, which is not equal in 0 to 0 in practice. So it is a consistent way of estimating the base factor. So to conclude, there is a package available on Python, and which is also in my GitHub. This method can be adapted to a lot of other robust statistics and can be applied to a lot of parametric distribution. And so I think there is a lot of work to do about the bridge estimator on given robust statistics and to apply it maybe in a real data world. So thank you all of you for listening. If you have any questions, don't hesitate.